Welcome to this lesson on system design. Today, we're diving into one of the most critical components of modern infrastructure, the load balancer. Imagine a restaurant with one waiter serving every table. On a slow night, that's fine. But on a Friday rush, the waiter gets overwhelmed, orders are delayed, customers wait forever, and if the waiter collapses, the whole restaurant stops. Now, imagine a host at the door who looks at all the waiters, sees who's free, and sends each customer to the least busy one. That host is a load balancer. In this analogy, the waiters are your servers, and the customers are incoming requests, like web traffic or API calls. A load balancer is essentially the traffic cop of your network, deciding exactly which server handles each incoming request to keep the system running smoothly. I'm Gibran, and today we'll break down how this works at scale. By definition, a load balancer is a system, either hardware or software, that sits between your clients, like users or browsers, and your backend servers. Its primary job is to distribute that incoming network traffic efficiently across all available resources in your server pool. Without it, you're at the mercy of a single point of failure. Think about a system without a load balancer. Every client talks directly to one single server. If that server crashes, you have a total outage. If traffic spikes, that server gets overloaded, leading to slow responses and timeouts. Most importantly, you can't scale beyond what that one single machine can handle physically. In this scenario, we have a single point of failure. If our server goes down, our users are left with nothing but error pages. This is why we move toward horizontal scaling, adding more servers to handle the load instead of just making one server bigger. But to do that, we need a way to manage those connections. This is where the load balancer shines. By placing it in front of a pool of servers, traffic is spread across multiple machines. If one server dies, the load balancer simply stops sending it traffic, and the others keep serving the users. This allows you to add or remove servers seamlessly as your traffic grows. As you see here, the clients never talk to the backend servers directly. They only know the load balancer's address. This separation gives us three core benefits: high availability, because there's no single point of failure; scalability, as we can add servers on the fly; and improved performance, since no single server is overwhelmed. High availability is the gold standard in system design. By using a load balancer, we ensure that even if a data center or a specific rack has an issue, our service remains up. It's the difference between a minor internal alert and a front-page news outage. Now, let's look at how this fits into the overall architecture. In a typical production environment, the load balancer holds the public-facing IP or DNS entry. The backend servers sit in a private pool, often unreachable directly from the public internet. The LB continuously monitors the health of these servers and only routes to the healthy ones, making the whole process invisible to the user. One of the most common questions in interviews and exams is the difference between Layer 4 and Layer 7 load balancing. This refers to the OSI model layers, where the balancing decision is made. It's essentially a choice between speed and intelligence. Let's break down the technical differences between these two types. Layer 4 balancing works at the transport level. It makes decisions based on the IP address and the TCP or UDP port. It doesn't look at what's inside the packet, it just cares about where it's going. Because it does less inspection, it's incredibly fast. It's great for raw TCP traffic or database balancing. Layer 7 balancing happens at the application level. It actually looks at the HTTP request. It can see the URL, the headers, or even cookies. This allows for intelligent routing, like sending requests for images to one set of servers and API calls to another. It's slightly slower due to the inspection, but far more powerful for web apps. To summarize the comparison, L4 balances based on the address, while L7 balances based on the content. Think of L4 as a mailroom sorting by zip code, while L7 is a personal assistant reading the letter to decide who should handle it. Both have their place depending on your specific performance and routing needs. Now, how does the load balancer actually pick a server? It follows a specific algorithm. There isn't just one way to do it. The right choice depends on your server capacity and the nature of your requests. Let's look at the four most common algorithms used in the industry today. First is round robin, where requests go to servers in rotation, simple, and effective if all servers are equal. Second is least connections, which sends traffic to the server currently handling the fewest active connections. This is much better when requests take varying amounts of time to process. Then we have weighted round robin, where you tell the LB that certain servers are more powerful and should get more work. Finally, IP hash uses the client's IP to ensure a user consistently hits the same server. This is useful for sticky sessions, where session data is stored locally on the server. Load balancers aren't just distributing traffic blindly. They are constantly monitoring the backend pool through health checks. Every few seconds, the LB pings the servers, maybe a simple get/health. If a server stops responding, the LB marks it unhealthy and stops sending traffic there immediately. This mechanism is what enables zero downtime deployments and automatic failover. When the server recovers, the health check passes, and it's automatically added back to the rotation. This level of automation is why load balancers are the backbone of any reliable, high-traffic system you use today. In the real world, you'll encounter software balancers like NGINX and HA Proxy, or cloud-native options like AWS's Elastic Load Balancer. Even CDNs like Cloudflare act as global load balancers. Every time you use Netflix or Amazon, a load balancer is making a split-second decision for you. That invisibility is the hallmark of a great design. To recap, load balancers solve bottlenecks and single points of failure by distributing traffic. You choose between L4 and L7 based on your needs, use algorithms like round robin or IP hash to manage the flow, and rely on health checks for zero downtime reliability. These are the fundamentals of scalable architecture. Thanks for joining this introduction to load balancers. Keep these concepts in mind as you build your own scalable systems. I'm Gibran, and I'll see you in the next lesson.